Hello everyone, now I'm going to show how to make binary trees in Lua. So binary trees are data structures wherein it's like a data structure which forms a tree, and there'll be a root which is the initial value, and there'll be multiple branches having different nodes. So in each node they may or may not be branches in them, and usually in binary, and we should always it should be always there should be no extra branches, there should be no more branches than two. If there are if there should be only two or one or no branches. So the topmost the initial value of the tree is called the root, and the end at the and the extreme values at the end of the tree is called leaves or leaf. So now if we see in the code, we create a class called node as a dictionary value, and we have an index method called node, and here we will be initializing the class you can take any name such as init or something like constructor, but here I've used new, and it takes a parameter value. And in local self set meta table, this will help us in the inheriting of values from the node. So usually, and also for the value, we have assigned it the value what we have defined, and the self dot right is nil, and the left is nil because we have not yet defined, and it always returns the self local variable self. So there are various functions in this program. There is size, there is branches, there is height, equal is isomorphism, which I'll explain further later. Pre-order, post-order, in order, minimum, maximum, and the print root to leaf paths. So first we create two trees. One is root and another one is root 1. So here the root value is 12, and the other branches are the other nodes are 7 and 13. So root dot left is the left side of the left branch of node 12, which is the root 12, and 13 is the right side of the branch 12. And then in the left branch of the roots left again, so the what is the left node, which is 7, and in that 7 it's 7, and 7's left node left branch will be 113, and its right node will be 72, and 13's left node will be 12, and right node will be 20. And again we have one more value, which is root dot right, which is 12's 12's node, which is 16. So we'll print value of root node, which will print the root dot value, and which will just print the root's value. And root tree 2 is just similar, is the same copy of root 1, because for testing purposes, for demo purposes in the later on check conditions, we can later on modify this to see how the branching happens. So in function size of node, it's a recursive function, and mostly this program is related to recursion. So recursion is nothing but calling a function within itself. So what we do here is we add 1 to the size of the node dot left. So we are again calling the size of the we're again calling size inside the function size, and we take the value, the left value, and for the right too we take the size of the right side. So this will just count the number of nodes in the tree, and for branches it will count the total number of branches inside the tree. So if the node if node left exists, then it will increment the count by 1, and if right exists, it will increment the count by 1. And again recursion happens here, but we're incrementing it by the count with the branches of node dot left and branches of node dot right. So this returns the height of nodes, not the edges. So what it does is it prints the uh, tallest tree in the tallest tree of the two, or else it will just return 0 for that smaller tree. So what we do is that we take the maximum value of the height, and we again call height inside height again. We take the node dot left, the left branch, and again if there is another node inside that, we take again the node dot right and node dot left again. So visualize underscore centered root is nothing but printing the entire tree with some ASCII art. So to understand how the tree appears, we use the backward slash and some space indentations. So what we do is we uh, we start calling the function height inside visualize underscore centered with the root name, the root value, and for q we create a table with the name of root, and level will be 1. So you can't keep the level as 0 because first level will be 1 in the tree. So this while loop will keep iterating until the length of the queue is greater than 0 and the level is lesser than the height which we got from the function height. Then local next underscore level is an empty table. So string dot repeat will repeat the the single space, and the value will be 2 raised to the height minus level. So for exponents um, we use this caret symbol, and line is equal to an empty string. And here inside this for loop, what we'll be doing is we will be adding the value next level to the when queuing the values using table dot insert, and then we will print the lines. Then we have the arrow underscore line, which is for the backslash and the indentations. So this first loop will just print the uh, nodes and leaves in order. So the second loop is just uh, for the backslash and the arrow marks, and the like how we have the for the branches we draw slashes, we use these slashes, and we use indentations, and then we print the arrow underscore line. So we will increment we will assign q to next level, and level will increment by 1, so that it will keep iterating in the while loop. And then function equal tree1 comma tree2. So this will check if both the structures are equal and have the same values. So if we just change it, if it even change one value in the tree one root 1 or root root, the value will show false. So it's just boolean output, no yes or no, like string. And then we have this isomorphism function. So isomorphism is nothing but nodes having the same values, but the branches are swapped. um, but they can be at any level. So we compare them using two trees, tree 1 and tree 2. If not tree 1 and not tree 2, then it will return true, which will say it is it's a proper tree. If it's not proper, that one of them does not exist. And then we have tree 1 and tree 2, uh, which will check else if dot value is not equal to tree dot value, then it will return false. Local case 1 is equal to isomorphism tree 1 dot left, tree 2 dot left, and isomorphism tree 1 dot left and tree 2 dot left to tree 2 dot right is again a recursion function. And case 2 is again another recursion, but it's for the different uh, branching. Like as a reswap, it'll swap those values, and it'll return case 1 or case 2. So above the isomorphism is the equal function, which I showed you before. So that uses recursion. And then we have pre-order. So pre-order is nothing but it will go from left to right till it'll first go from the root, and then from left and again to right. So it'll keep reading the nodes and print those values in the pre-order format. So it just prints them in a form of a list, but not any like how we have the visual underscore center function. We just print them in this manner. So in post order 2, we here we have different method of reading. We first go to the left value, then the right value, and then the root, and again from the root we go to the left value of the branch and go to the right value of the branch. So then here we have in order. So we sort the values using values by reading them first the left node, the right node, then we go up, then we read the right node, then we go to the right tree, and so on. Then this is minimum, which will find the minimum value of the tree. If minimum and minimum left is greater than current minimum, then so you can just bring these down. So you can see that here we have two values, which is minimum left and minimum right, which will call the function minimum again. It's a minimum function itself. So node dot left and no will take the values node dot left and node dot right. So we'll recursively keep on going down the branches further and further deep inside the branch inside the tree until we reach the end of the tree, which is the leaves. So here we have current minimum is equal to minimum left and minimum right. Here we have again uh, if minimum right is and minimum right is lesser than current minimum, we will assign the current minimum to the right side of the value. So we will return only the current minimum and maximum is the same thing, but we just have the change of symbols. We have greater than and lesser than, less greater than in this one, but lesser than in the other, in the upper case, in the minimum case. And then here we have the print root to leaf paths, which will print the leaves, will print the root from the leaf to the, from the root to the leaf. So we have this path variable, which is an empty table, or it may be the path we specify. We will insert the values path, the node value. If node dot left is if not, if not node dot left and node dot right, then path colon table dot concat, which will join the path value along with the arrow mark symbol. So we have this, we take this arrow mark, and then we have print root to leaf paths node dot left comma path, and which is a recursive function again. And then we will be deleting the values for temporarily for backtracking. And then in output we have size of the tree, which will so this is just nothing but the size of the tree, which we will execute all the functions in the bottom of the code. You can even use the make files to run these. It's your choice, however you want you could do it. So what, before doing anything else, we'll just run the program. So what is happening here is so we have value of the root node, which is 12, which is printing the root value of the node 12, and in and even in the root 1, it's 12, because there's the same. Size of the tree is 8, and again root 1 is size 8. Number of branches in the tree is 7. Height of the binary tree nodes is 4. And then we have one more and then we have path, which will print the path. So first we had 12, we go to 7, we go to 113, and this path is popped. And then we have one more path, we go to 12, we go to 7, and we again go to 72. That path is gone. Now we go to 12 again, we go to 13, and then from 13 we go to 12, because we read from the right side. And then if there is nothing, it will just if there is something there, it will just keep on going forward. If not, it will just pop. If not, it will just finish the search and then pop the entire path. And then we go back to the final path, which is the leaf 20. So maximum value in the tree is 113, minimum value in the tree is 7. Then in order traversal, so as I said, we read from the uh, left right to the branch, and again again go to the top, and again come back and print them, just like how we had the path. So we have 113, 7, 72, 12, and then we have 16, which is right here. There is a kind of a problem at the indentation. 16 kind of comes down, but if you add more values, if you add more branches, it will perfectly align. The values will get perfectly aligned. And then this is the post order traversal. So what we do is we first go 130. We read this from the uh, left right to left. So we read from 113, 72, and again come back here, and we again print 7, and we again go down here 16, 12, 20, again come back here 13, and return to the root. And are the two trees equal? Yes, it is true. And are the two trees isomorphic? Yes, it's true, because if you flip any of the branches, it's still same value. So we'll just change the values. We'll just make them something like, no need of this line. We'll make some modifications for the values. And now it shows false for the isomorphic and the equality, so those both values changed. So yeah, later on I'll explain how graphs work in Lua. Thank you.